So now let's start the next topic, that is partial order relation, or in simple words you can call it partial order. The another word you can call it partial order relation. In short, we will call it POR. Okay, so first let's understand this word order. So from where basically these, okay, these are called order relation. Now let's understand this. Sometimes, tell me, set is unordered collection, right? Yes or no? This set we have studied, and this is unordered collection of elements. For example, okay, I can say TOC, theory of computation, discrete mathematics, and I can say, okay, compiler design, I can say digital logic and computer organization. So you can clearly see that this is a set, right? This is a set of 5 subjects in the GATE syllabus. Right now we are studying discrete mathematics. After this we will study digital logic, theory of computation. All these subjects we will study. But the point is, this is a set, and this is unordered, right? So this set of subject, this is clearly unordered, correct? Yes or no? This is clearly unordered. Because set is unordered collection. Set is unordered collection of elements. Now let's assume that you are starting your preparation. Okay, this is a new aspirant. So let's assume this is a new aspirant. Tell me, for new aspirant, if okay, new aspirant of GATE, so he doesn't know about this. Okay, so let's assume in the BTech he has not studied anything, so he does not even know the full form of these subjects. He does not even know the syllabus of these subjects. So he is a new GATE aspirant. Okay, so let's call him GATE aspirant M. Now you can notice that what M. So tell me, this set, if you give this set to this aspirant M, is it useful? This is not much useful, right? Okay, because this new aspirant does not know how to start preparation, in which order to study subject. This is a question, right? For this new aspirant, what is the question in his mind? The question is coming. Tell me, what is that? In the, okay, in his mind there is a question, and what is that? The question is like this. Okay, in which order to study these subjects? Okay, which order to study? In which order to study? So this is the question is coming. Now you can notice here. So this word order, notice, okay, just notice this word order. So this aspirant is thinking in which order to study. So basically on this set we need to put some ordering, right? Yes or no? So let's assume this aspirant has come to Go classes. So okay, now this aspirant has come to Go classes, and now this aspirant is asking in which order to study. This question is asked, this aspirant is asking this question to Go classes, in which order to study these subjects. Now you can notice that this set is unordered collection, but we need to put some ordering on this set. How to do that? We need to put some ordering on this set. My question is how to do that. So this Go classes, what it will do? It will try to put some ordering on this set. Okay, what it will do? It will try to put ordering on this set. Okay, on this set, let me call it this set S. On this set S, we will try to put some ordering. But how to do that? How to put this ordering on this set? So what we can do to put this ordering, we can define a relation. Okay, so basically to put order, okay, on set S, what we can do? We define a relation. We can use relation. So this relation concept is very important. You can notice this relation concept we use to put order on set S. So to put order on set S, we define a relation. A relation we define, and that relation we call it prerequisite. Let's call this relation prerequisite relation. Okay, this relation we call it prerequisite. What I mean, I can say in this relation R, let me call it prerequisite relation, and in this relation R I am doing this. X is related to Y if and only if X is a prerequisite of Y. Is this clear to everyone? So on this set of subjects, I am defining this relation. I am defining this relation prerequisite. I am saying that X is related to Y if and only if X is a prerequisite of Y. So far, is it clear? Tell me, is this clear so far? This is what I'm doing to put ordering on set S. I'm defining a relation on set S, and this is the relation I'm defining. X is related to Y if and only if X is prerequisite of Y. Using this relation, what will happen automatically? Okay, this student can get ordering of this subject. This is the question of this student. How to, okay, in which order to study. Now what I have done, what this Go classes has done, Okay, we have put this relation, we have defined this relation on this set, on this set. Now what will happen? Because of this relation, what will happen? Discrete mathematics is prerequisite of what? Tell me. Discrete mathematics is prerequisite of TOC. TOC is prerequisite of compiler design. Correct? TOC is a prerequisite of compiler design. And you can notice digital logic is prerequisite of computer organization. So these things we have. Do you agree? Discrete mathematics is prerequisite of TOC. TOC is prerequisite of compiler design. Digital logic is prerequisite of computer organization. I can see because before TOC you should study discrete mathematics. Before compiler design you should study TOC. So before compiler design you should study discrete mathematics. Okay, correct? So I can say discrete mathematics is prerequisite of compiler design. So this is what we have. Okay, this is what we got. Now you can notice we got an order. If you notice, because of this relation, because of this prerequisite relation, we have got order. What order we got? So now this student M, to this student M, we can give an order. This order we can give. We can say that discrete mathematics is related to TOC. Means discrete mathematics must be done before TOC. Okay, and TOC is related to compiler design. So first you should do, so before TOC, you should definitely do discrete mathematics. Before compiler design, you should definitely do discrete mathematics, correct? Also, digital logic you must do before computer organization. So basically this is what we got. Did I give complete order to this student? Did I give complete order? What this student will tell me? What this student will tell me? Tell me, what is the next question this student will ask? This new aspirant will ask. What is the next question? See, I told him, okay, before TOC you should study discrete mathematics. Before compiler design you should study TOC. Before computer organization you should study digital logic. But the question that this will ask, he will ask, this is a partial order, right? This is not a total order. I did not give total order. Because the question that we will ask, what is the order between these? Yes or no? This is the question they will ask. What is the order between these? Like, what is the order between these? What is the order between these? This is the question this aspirant will ask. Do you agree? Yes or no? So basically, I can say this is a partial order. Can you notice this is not a total order? This is a partial order I have given. I did not give him total order. I gave him partial order. Do you agree? Yes or no? I have given partial order. I did not give total order. So this aspirant M, he does not have total order. He has a partial order. Now from this partial order, I can say that only this is the order. Okay, now you can do anything with this order. So from this order, he can create his own partial order, total order, whatever. From this information, what he can do, what this aspirant can do. Tell me what this aspirant, like in the real life, just think logically. What you will do if I give you this thing, like let's assume this is the thing I give you. So this is the thing is given to M, then what you will do? Then you can create your own total order from this. Can you create like this? Can you study like this? Is it correct? From this is a partial order, but now you can create your own any of the total order you can create. Like, can you create this from this partial order? Can you study subject like this? Is it correct? Can you study subject like this? Can you study subject like this? In which order can you study subject? Which of them is correct order? Which satisfy this? Which satisfy this? So this is also fine, this is also fine, but this is not fine. Definitely this is not fine, right? So are you getting my point? So this relation, this prerequisite relation we defined, this relation has given us partial order. This did not give us total order. This gave us partial order. Why this is partial order? Because you can notice there is no order between these two. There is no order between these two. So I can call it partial order, not a total order. This is not a total order. This is not a total order. This is a partial order because there is no order between these two. There is no order between these two. So this is the idea. Is this idea clear? Remember, I am not telling you, I am just teaching you intuitively. Can you understand intuitively like what is happening here? Set is unordered collection. Set does not have any order. But sometimes in the real life, we want order, right? Yes or no? For example, let's assume there is a parent and they did not study. These parents did not study. So let's assume this is a parent. Let me call it, okay, let me call it P, and this is female, and let me call it Q. They did not study, but they want their child to study. Okay, so let's assume they have a child. Now, okay, so these are the parents. Let's call them these are the parents. These are uneducated parents, and they have a child A. This is the child. Now they want this child to study, so they go to a school. Okay, these parents, they go to a school, and they ask this school in which order this child should study. They don't know. Let's assume they do not have any information. They don't know what is the first class, what is the third class. Let's assume. Okay, let's assume they don't know about what is the 10th class, what is the 11th class. They don't know. So they go to this school and they ask in which order to study. Okay, now this is the, you can notice first class, second class, third. I can say that this is what we need to do in the school, right? Like we need to study 12th class, 11th class, okay, first class, second class, fourth class, okay, third class, fifth class, like this, correct? Yes or no? This type of thing we have. Ninth class, fourth class, something like this. So these are the classes we have to do. Basically, these are the classes that we have to study. Now, okay, but these are unordered. This set is unordered. Now, what this school will do? This school will define, this is the set of classes. Let me call it C, or let me call it whatever R. Let me call it set A. So this is your set A. This is the set of all the classes. Now, on this set of classes, this is unordered. There is no order here. So these parents will ask in which order to study these classes. Then what this school will do? This school will define a relation. This will define a relation. This will define a relation on this set A. And what this relation will define? They will define like this. X is related to, okay, so they will define a relation R on set A. X is related to Y if and only if X to be done before Y. X to be done before Y. Okay, so this is the idea. Now tell me, because of this relation, will you get total order or will you get partial order? Will you get total order or will you get partial order? So you can notice on this set A, this is the relation we are defining. We are saying that X is related to Y if and only if X to be done before Y. So you can clearly see that now you will get a total order. Because of this relation R, I can say this relation R gives total order. This relation R will give total order on set A. What will happen? You should do first class before second class. You should do second class before third class before fourth class before fifth class, and so on. Okay, and finally 12th class. So this relation has given you total order. This is called total order. This is called total order. Why this is total order? Tell me. Can anyone tell me why this is total order and why this was partial order? This was partial order. You can notice this is partial order. Why this is partial order? Because there are elements between which there is no order. Yes or no? We have at least two elements between which there is no order. Correct? Okay. There is at least two elements between which there is no order. But here, between every element there is, okay, between every pair of elements we have order. Right? Yes or no? So this is the idea of order. I hope this concept is clear. Why this concept is very important. This partial order. Why we study this concept. What is this concept? This is basically, we want to order the elements of a set. The idea is very simple. Set is unordered collection. So whatever set you have, in that set, you don't have any order. We want, in the real life, we want order on elements of set. Sometimes this is very useful. Okay. So that's why what we do, we define relation on a set. So you have a set. This is the simple idea that you have a set. And this set is definitely unordered. This set is unordered. Now what we want, okay, to get order, to get order on elements of A. What you do? Tell me. Elements of A. So what will you do? If you want to get order on set of on elements of A, then what we do? Then we define relation. Then we define a relation. Okay, then we define a relation on A. Now tell me, this order you want, okay, my question is, which properties this order should satisfy? This is my question. So which properties this order should satisfy? Which properties this relation should satisfy? Or I can say, which properties this relation should satisfy, so that we can get an order. This relation should satisfy. Which properties should this relation satisfy, so that we can get order? Okay, tell me, is symmetric property, like, would you like, if I give you symmetric property, then is it useful in the order? When you are talking about order, when you are talking about order, then symmetric property is useful or not? Okay, first you tell me, is symmetric property useful? Is the symmetric property useful when you want order? Remember, you want order, you want order of elements, you want order of elements. Okay, then tell me, symmetric property is useful? No, symmetric property is not useful. Just think about it. Symmetric property is very bad actually. This is very bad. Just think about it. If I tell you that before compiler design you should do TOC, and before TOC you should do compiler design, before compiler design you should do TOC, and before TOC you should do compiler design, isn't it confusing? Yes or no? This is confusing, right? You can never start your preparation. You can never start, like, before compiler design you should do TOC, before TOC you should do compiler design. So this is a mess, I can say. Okay, so this symmetric property definitely is not needed. Is anti-symmetric property useful? Is anti-symmetric property useful? Anti-symmetric property is definitely useful, because if you have two different elements, then okay, you should never have this type of situation. This type of situation should you never have. Between different elements you should never have this type of situation. So anti-symmetric property we definitely want. Yes or no? Agree? Between different elements, this type of situation we don't want, because I can say between different elements, I can say between different elements A comma B, we don't want we don't want this type of situation. We don't want situation. Okay, so that's the reason anti-symmetric property is useful. Definitely anti-symmetric property is useful here. Okay, next, tell me the next. So anti-symmetric property useful. What is transitive property useful? Is a transitive property useful when you want order on elements? Then is transitive property useful? Definitely transitive property is useful, because see, just think about it. If you are going to study discrete mathematics before TOC, if you are going to study TOC before compiler design, then automatically you should study discrete mathematics before compiler design, correct? Yes or no? You should study discrete mathematics before compiler design, definitely, correct? So I can say transitive property is definitely useful. So these properties are useful, you can notice. And now the last thing, okay, do we really need reflexive property? Do we really need reflexive property? Let me tell you actually, okay, we to be frank, we don't need it, but we want it. We want it. Why we want it? Let me tell you. Why we want this reflexive property? Let me tell you. Just think about it. Let's assume you come to me. Okay, why we want reflexive property? Let me just tell you. Why we want reflexive property? We definitely want reflexive property, but why we want it? Let me tell you this point. Okay, let's reflexive property. Okay, and the reason is this. Let's assume you come to me with 3 subject. Okay, so let's assume this is the new aspirant. You know, this is the new aspirant, and let's assume this new aspirant is coming to me. Okay, so let's assume this new aspirant is coming to go with these 3 subjects. Okay, these 3 subjects this aspirant has. So let's assume apti. Okay, this aptitude, and let's assume TOC, and let's assume the last subject is computer network. So let's assume these are the subjects. Okay, computer network, TOC, aptitude. Now they are coming to Go classes, and they are asking, this aspirant is asking in which order to study these subjects. Then what? Okay, then do we have any order here? We have any order here? You can notice there is no order here, right? We cannot give any order, because you do not have, if I define this Go classes, what it will do? It will define the prerequisite relation. We will define the prerequisite relation. And when we define this prerequisite relation, then you can notice that FT is not related to TOC, and TOC is not related to FT. Okay. Similarly, you can notice that TOC is not related to CN, and CN is not prerequisite of TOC. Similarly, you can notice FT is not prerequisite of CN, and CN is not prerequisite of FT. So you can notice actually. So finally, what we will give? So what we will give? Tell me. we will just simply say that there is no order. Really there is no order. Okay, if there is no order, then what this aspirant should do? See, now you can notice there is no, okay, no one is related related to no one. Now here we need reflexive property, at least reflexive property we want. See, no one is related to no one. FT is not related to TOC CN. TOC is not prerequisite of FT CN. CN is not prerequisite of TOC FT. So no one is prerequisite of anyone. Okay, but we want reflexive property. Why? Because, okay, you should at least start this subject, right? Yes or no? You should at least study these subjects in any order you study, but you should at least study these subjects. Without this reflexive property, basically you cannot even study. But what will happen with this reflexive property? At least you can study this subject in any order you want. Okay, so anyway, the point is simple, that you have this set, and this set is, let me tell you the actual reason what happens. This set is unordered collection. Sometimes what happens, if you don't have reflexive property, then there is a problem. But that is this, in this type of situation, what will happen, that this set will be gone. If you don't have the reflexive property, then this set itself will be gone. So that is the reason this reflexive property is desirable. Okay, so anyway, this is I hope this logic is not that much good. I tried to find this logic why we need reflexive property, but actually no concrete logic was given. But this logic that I told you, this logic is given on Stack Overflow by someone, so I told you here. Okay, so this is not much like, okay, intuitive. I don't know whether you understood this or not. Okay, so don't worry about it. The point is, this reflexive property is also desirable. But the important thing is anti-symmetric and transitive property. These are definitely we want. We don't want symmetric property, but we want anti-symmetric property, and also we want transitive property. And reflexive property is also desirable. Is this clear? If reflexive property is not there, then this relation will be empty. If reflexive property, if we don't have reflexive property, then this relation, this prerequisite relation, this relation will be empty. And because this relation is empty, so to this student, we are giving empty relation. Basically, we are giving nothing to this student. Okay, so this student cannot study. Anyway, the point is simple, that, so what is this? I can say, what is a partial order relation? So let me tell you, what is a partial order relation? Partial order relation is a relation in which you have these three properties. What is a partial order relation? So this is the final definition. What we have seen so far, that is just intuition for partial order relation. Did you understand this intuition, like somewhat? What is this partial order relation? Why it is needed? Why it is important? Why we study this? Okay, from where these properties are coming? This, okay, so basically partial order relation means these properties must be satisfied. Reflexive property must be satisfied, anti-symmetric property must be satisfied, and transitive property must be satisfied. These three properties must be satisfied for partial order relation. And I told you why, the reason. Okay, this is more and less desirable. Okay, so the reason of this is not much clear, but these are clear why we need anti-symmetric and transitive property. If you want order relation, if you want to put order of between elements, okay, then you definitely need anti-symmetric comma transitive. Of course, reflexive property is also needed. So the point is this, partial order relation means these three properties must be satisfied. We call them RAT properties. RAT properties. Okay, so this is the definition. In the equivalence relation, we have RST, reflexive, symmetric, transitive. In partial order relation, we have three properties which are, okay, so we have transitive property in the partial order relation. We also have reflexive property, and we also have anti-symmetric property. These three properties must be there. So this is the definition. The definition of partial order relation. It means a relation which satisfies reflexive, anti-symmetric, transitive. These three properties must be satisfied. Then we will call such a relation partial order relation. The another name of partial order relation. So I can say that if R, let's assume this R on set A, let's assume. So this is relation R. So this relation R, if I can say, if R on set A is a partial order relation, then this pair we call poset. Then this pair is called poset. This is just a terminology. What we are saying that if this relation R, if this is partial order relation, okay, then this pair A comma R means basically this type of pair, base set comma partial order relation. This pair is called poset. We call it poset, where this is called partial order relation, or you can simply call it partial order. Is this clear? Is this terminology clear? Now let's see some standard partial order relations. So okay, some standard, these are very standard, so you should understand them. Some standard partial order relations. First relation, this less than equal to relation. This less than equal to relation. So for example, tell me on set of natural number, this relation, is it partial order? So on, I can say on set of natural number, or I can say on set of integers, it does not matter. On set of natural number, this relation less than equal to relation. So what I'm saying x is related to y if and only if x is less than equal to y. So this relation, tell me, is this relation partial order? Is this relation partial order? So you can clearly see this is reflexive, because definitely a is less than equal to a. Okay, is this antisymmetric? Check these properties. Is this antisymmetric? Yes, definitely this is antisymmetric. Why this is antisymmetric? Because if a less than equal to b and b less than equal to a, then I can say a is equal to b. If a is less than equal to b, b is less than equal to a, then I can say that a is equal to b. And this is transitive also. This is a transitive also, because if a is less than equal to b, b is less than equal to c, then definitely a is less than equal to c. So all these three properties are satisfied. So definitely this is a partial order, I can say. So this relation is a partial order. So what I can say, definitely I can say on set of natural number, this relation, this complete thing, what we call it? Tell me what we call it? We call it poset. So this is a poset. I can say this is a partial order relation. This is a partial order relation on a set of natural number. Is it clear? Can you notice this is a partial order relation on every set, whatever set you take. This is actually partial order relation on every set of numbers you take. This is a partial order relation on set of integers. Okay, this is a partial order relation on set of real numbers. So whatever you take, whatever set of numbers you take, this is always a partial order relation. So this is the idea. Some standard partial order relation, this is less than equal to. This is a partial order relation. Now understand few things about this relation. So you understood that. So let's assume this is your set. Let me give you a set, and this set is 1, 2, 3, 4. Okay, so let's assume this set you have. On this set, I am defining this relation. Okay, so this relation I am defining. So then what I can say? Tell me. This relation I am defining. So I am defining a relation R. This is your set S, or this is your set A. So I am defining a relation R on A, and I am saying that X is related to Y if and only if X is less than equal to Y. So this less than equal to relation I am defining. I am defining a relation R, which is basically saying that X is related to Y if and only if X is less than equal to Y. You can clearly see this relation R, this is clearly reflexive, antisymmetric, and transitive. Correct? So this is antisymmetric and transitive. Okay, so all these three properties. So I can say that this is basically a, okay, so from this I can say that this is basically a partial order relation. This is a partial order relation. Now you can notice one thing. Will it give you order on these elements? Will this give you order on these elements? So you can notice 1 is related to 2. Okay, 1 is related to 2. I can simply write it 1 is less than equal to 2. Similarly, you can notice that 2 is related to 3. I can say 2 is less than equal to 3. I can say 3 is related to 4. I can say 3 is less than equal to 4. And remember, transitive property is also there. So I can say 1 is related to 3. I can say 1 is less than equal to 3. I can say 1 is related to 4. I can say 1 is less than equal to 4. So this transitive property is also there. From all these, can you see there is an order? We are getting an order. Actually, you can notice between every two elements you have an order, right? Yes or no? Can you notice between every pair of elements? This is the base set. Between every pair of elements, you have order. Correct or not? I can say that. I can say, okay, for any A comma B you take in the base set, you can notice that there is a order between A comma B. Yes or no? You can notice that definitely either A is related to B or B is related to A. Agree or not? Whatever elements you take. For example, if you take 2 comma 4, then you can clearly notice that either A is related to B or B is related to A. You can notice 2 is related to 4. So whatever two elements you take, there is an order between these two. Whatever elements you take, whatever two elements you take, there is an order between these two. Either A is related to B or B is related to A. This will happen. Whatever two elements you take. Correct? So this is the idea. So this relation, this is the standard relation, less than equal to. This is a partial order relation. And what this will do, this will give a ordering on the elements of the base set. So on the elements of the base set, this order we get. Okay, this is the set. This is the set. And because of this relation less than equal to, what we got? We got ordering. I can say 1 is less than equal to 2, 2 is less than equal to 3, 3 is less than equal to 4. This is called ordering. Ordering of elements of A because of this. So this is called partial order relation. Is this clear? Remember, for partial order relation, all you have to do is just check these three properties. This is what you have to do. Next, the next is our greater than equal to. Tell me, greater than equal to. What about greater than equal to? Tell me, what about greater than equal to? Is this partial order relation? Is this partial order relation? Yes, this is also partial order relation. You can just check. This will also satisfy all the properties. So this is also partial order relation, greater than equal to. Okay, so for example, I can say 1, 2, 3, 4, and I am defining a relation on. So I am defining a relation on set A, and I'm saying that X is related to Y. X is related to Y if and only if X is greater than equal to Y. So you can clearly see that 2 is related to 1. Can I say 1 is related to 2? You can notice 1 is not related to 2, 2 is related to 1. 3 is related to 2, 4 is related to 3, and there is transitivity because partial order relation is transitive. Okay, this is reflexive, this is anti-symmetric, and this is transitive. So because of transitivity, what you can say? You can also say 3 is related to 1. You can also 4 is related to 1. 3 is okay. So 4 is related to 2, like this. So this is the idea. So this ordering you got. What ordering you got? Tell me what ordering you got. I can say 4 is greater than equal to 3, greater than equal to 2, greater than equal to 1. So the relation is greater than equal to. This is the relation. And this is also partial order relation. Next, what is the next special relation? That is subset relation. Next relation is subset relation. This is subset relation on power set of A. This is subset relation on power set of A. And so remember, if I give you a set A, for example, let's assume this is the set A comma B. Now, what is the power set of A? On this set, can you define this subset relation? Tell me. On this set, can you define subset relation? On the elements of this set, can you define subset relation? No, you cannot define, right? On the elements of this set. On this set, I cannot define element, right? Yes or no? Do you agree? On this set, I cannot define subset relation. Just think about it. How can I define? Like, this does not make any sense. This does not make any sense, right? So on this set, we cannot define this subset relation. So what I can do, I can find power set. I can find power set of A, and on this power set of A, on this set, what we can define on power set of A, we can define relation R. So this relation R we can define on power set of A like this. X is related to Y if and only if X is a subset of Y. Now this is correct. Yes or no? Did you understand this? What I am saying? Okay, this is my question. On this set, can you define power set? On this set, can we define subset relation? Can we define subset relation? What it means? See, this is your set. This is your set. This is your set. Remember, your set is 1, 2. This is your set. So can I define a subset relation? Can I define a subset relation? Can I say this is correct? Can I say is this correct? Is this correct? Is this correct? No, these are not even set. This subset, this is defined only for set. So this is not correct. So can we define subset relation? The answer is no, because it does not make any sense. It does not make any sense. This is not correct. This is senseless. Basically, this is nonsense, I can say. Again, here I can say this is a nonsense. So the idea is this. Okay. So on the power set, now you can define the subset relation. Can you notice? Yes or no? Now you can notice. So this is your power set of A. This is the power set of A. You have 5, you have 1, you have 2, you have 1, 2. And this is your power set of A. And you have 5, you have 1, you have 2, you have 1, 2. Now you can define the subset relation. Now you can very easily define the subset relation. So you can notice that this 5 is related to everyone. 5 is subset of everyone, right? So you can clearly see 5 is a subset of 5. 5 is a subset of 1. Actually, 5 is a subset of 2. So this subset relation you can define. Similarly, you can see that this 1 is subset of 1. Okay, and this is subset of 1, 2. Okay, and this is subset of this. And this 2, I can say this 2 is subset of this and this. So this is the idea. Now tell me, is this a partial order relation? So far, I am only discussing partial order relation. After some time, I will discuss total order relation. What is partial order relation? How to check? Just check these 3 properties: reflexive, antisymmetric, and transitive. Don't worry about total order relation. Do not worry. Don't worry. In the next lecture, okay, by the end of this class, I will discuss what is total order relation. So don't worry about it right now. In the next lecture, this will be clear. Partial order relation means just check these 3 properties. So the idea is this. Tell me, this subset relation, is this reflexive? So if you have power set of A and this subset relation, now tell me, is this reflexive? Is this subset relation reflexive? Yes, definitely it is reflexive, because every set, you can notice, yes or no? Because every set is a subset of X. Second, you can notice this is antisymmetric, right? This is antisymmetric. Why this is antisymmetric? Because if X is subset of Y and Y is a subset of X, then what can I say? If X is subset of Y and Y is subset of X, then what can I say? Then I can say X is equal to Y. So this is antisymmetric. Is it transitive? Is this transitive? Yes. If X is subset of Y and Y is subset of Z, then I can clearly see that X is subset of Z. Okay, so this is transitive also. So you can clearly notice that this is a poset, because this subset relation, this is a partial order relation. Okay, so this is the idea. So this is also another partial order relation. What is this? Superset relation. Is this partial order relation? This is superset. Yes, this is also partial order relation. This is also reflexive, antisymmetric, transitive. All these 3 properties are satisfied. So this is also correct. Okay, and the next one, that is divisibility relation. This next one is divisibility relation. What is this? This is saying that basically, if you have a set, let's assume you have a set of natural number. Okay, this divisibility, or I can say divides. You can either call it divisibility or I can say divides relation. Basically, on a set of natural number, I am defining a relation R on set of natural number, and I am saying that X is related to Y if and only if X divides Y. X divides Y. Okay, so this symbol, this is the symbol for divides. If you remember, I told you a few things about divides relation. What is the okay? Tell me, what is this? Is this true or false? So this is a true. I told you these things. And what is this? And what is this? This is true. I told you this. If you remember, in the first lecture, I told you. Okay, so this is divides relation. The answer will be true or false. Here, answer will be false. Okay, so don't say that. Okay, so okay, here don't say that answer is true. Don't say answer is true. That is this. So this is divides. This is a relation. This is a divides, and this is a relation. This is a relation. So the answer will be either true or false. And this is an operation. I can say this is a number theory operation. Now, so let's come back to this point. So this relation I am defining on set of natural number, and I'm saying x is related to y if and only if x divides y. Okay, so tell me, is this reflexive? Is this divides? X is related to y if and only if x divides y. First, you tell me, is it reflexive? Definitely it is reflexive because x divides x. Next, is it anti-symmetric? Is this anti-symmetric? Yes, this is anti-symmetric because if x divides y and y divides x, then definitely I can say x is equal to y. If x divides y and y divides x, then definitely what we can say x is equal to y. Similarly, is it transitive? Is this transitive? Yes, this is transitive because if x divides y, y divides z, then I can say that x divides z. So this is all these three properties. So this divides. This relation, if you notice, this is a partial order relation. Okay. So these are some standard relations. Similarly, remember, if you remember, this less than equal to, if this is also partial order relation, this is also partial order relation. This is also partial order relation. This is also partial order relation. This divides is partial order relation. So what should I write here? Which another relation is partial order? Which another relation is partial order? That is multiple. That is multiple. So basically this relation, if you notice, this is also partial order relation. I can say relation R on set of natural number. I can say that x is related to y if and only if x is multiple of y. If and only if x is multiple of y. Now this relation R is also partial order relation. All you have to do, just check reflexive, antisymmetric, and transitive. These three properties you need to check. So this is the idea. Reflexive, antisymmetric, transitive. This is the idea behind partial order relations. Okay. Total order relation we will study in the next class. So right now you don't have to worry about total order relation. Why this word partial is coming, I told you. Yes or no? Because of these three properties, this word partial is coming, and the reason I already told you, but we will again see in the next class when we study total order relation. Okay, at that time this will be clear. Anyone has any doubt, you can ask. Hello, yes, Pratik.
Hello, yes, in that when you said that partial order relation is reflexive, can you explain that again? That I'm not able to understand.
Okay, there is nothing to understand there. That is not a mathematical concept. I am just telling you
Okay.
like some intuition. Like how can you basically this partial order relation? This is used to put ordering on the elements of a set. A set is an unordered collection. Okay, so the elements of a set, they do not have any ordering. But sometimes what we do in the mathematical applications, like in artificial intelligence or sometimes in the program also, what we want a ordering on the elements of the set. We don't want unordered elements. You can notice, okay, in your programming, whatever data structure you use, most of them are
Array
basically
and
ordered. Yeah,
yeah,
most of them have some order. Okay, so like there is a first element, there is a second element, there is a third
yeah.
element, like you can like most of them. Okay, so the idea is this, that most of the time we want ordering on the elements of a set. Then for that, what we can do, we can define a relation on the set. Okay,
Yeah.
so this relation, if you are using this relation to put ordering on the elements of a set, then this relation should have some properties, and these properties are basically anti-symmetric property. You don't want symmetric property, I told you. Okay, because symmetric
Then there will
property,
be confusion.
there will be a confusion in the symmetric
Yeah.
property. So you don't want symmetric property, you want anti-symmetric property. Okay, and similarly you want transitive property,
Transit.
and reflexive property is desirable. Let me also tell you, there are some authors, okay, there are some authors which don't include this reflexive property in the definition of partial order relation. So don't confuse yourself. That is the reason I'm telling you this reflexive property. Most of those authors, almost 99% authors, they include reflexive property in the partial order relation. But there are some authors, one or two authors, okay, who don't include reflexive property in the partial order relation. So that's the reason. Antisymmetric and transitive, these you need to understand. like, okay, why these are desirable. Reflexive property, just remember, like,
Yeah.
memorize. Okay.
And so in that one, there was one example in which the total order was there. Like we know what the order totally was. So
In the next
how's
class, in the next
how's
class, I will discuss the total order. Basically, I just gave you some intuition. I did not teach you concept at that time when I was taking these examples. This
okay,
new
okay.
aspirant example, okay, new aspirant is coming to us, okay, and asking for order on the subject. This is an analogy. This is called analogy. This is not a concept. Okay,
Okay,
this is
okay.
just to give you some idea of the concept, of the upcoming concept was about to come. Before that, I just wanted to give you some idea. I just wanted to give you some motivation, like why we study this partial order relation, why these properties are coming, why we want anti-symmetric property. In the equivalence relation we want symmetric property, but in the partial order relation we want anti-symmetric property. Why this? Okay, see, mathematicians are not, no, they are not brainless. Okay, they don't randomly do things. If they are defining partial order relation and they are putting these three properties, then there is some reason behind it. That
Yeah.
reason I wanted to explain. So that is the that is so that area is just for motivation. Okay.
Okay,
In the
okay.
next class I will tell you what is total order relation, the definition, the formal mathematical definition of total order relation we will see in the next class. The mathematical definition of partial order relation we have already seen. The mathematical definition says that you have a relation on a set, and if these three properties are satisfied, then we will
And
call it
it's for
partial order relation.